Our next speaker is Dr. Shruti Kuriyakose. Good. Her presentation will be about functional nanosystems manufacturing, and she's from CSIRO. Oh, what am I? Sorry. She's from Functional Nanosystems Manufacturing, CSIRO Linfield. I wrote this program, can you imagine? And her presentation will be about using direct radiography to create PMMA pillars for strongly coupled DBR mirrors. Looking forward to your presentation. The stage is yours.
Morning, everyone. I am Sruthi from CSIRO. I'm a postdoc fellow on the manufacturing unit. I'm based in Linfield City. So I will take you through my talk today. I have direct right lithography, create some PMMA pillars as a collaboration project with ANU University. Before I get into it, I would like to begin by acknowledging the traditional owners of the land that we are meeting today and also online. Pay my respect to the elders past and present. So the overview of the talk, I will take you through the DWL system that I've used is Nano Fraser. The design that I've used for the patterning, the thermal scanning probe for and the thermal scanning photolithography process that I have used. And I'll also share some initial results of the testing of the device and also share the future work that we have planned. So the direct right lithography system, Nano Fraser, is what I've used. That is the Nano Fraser Explorer that we have on site in Linfield. We got it from Nano Vacuum people. I saw James somewhere, but now I don't see him. Yeah, it was from them. So the Nano Fraser, it's a non-invasive micro-nano lithography equipment where it uses a bilayer resist stack, and the top layer of the bilayer is thermally sensitive. You can also use this system for the E-beam sensitive materials, where the sensitive material is protected by the second layer of the bilayer resist stack. There are two ways we can pattern the substrate using the Nano Fraser Explorer. The first one is laser scanning photolithography, where you have the laser 405, which is directly ablating the top layer of the bilayer resist. The resolution for this is for a larger dimension of the pattern that you want. Imagine connecting wires or electrode pads for your device. The second one is thermal scanning photolithography. So this is using a AFM cantilever and a tip. So what happens here is when you trace the pattern, the tip is hot. So you are able to ablate, according to the pattern, the top layer of the resist stack, and that is the hot. When the tip is hot, that is the trace pattern. When you come back, as in when it retraces, the tip is cold, where you can actually acquire the image. So this system is allowing you to validate your design then and there as you are patterning your substrate. So that information is fed back in a closed loop feedback system, which is then going to adjust your design, and you are able to get an optimal patterning during the process. This thermal scanning lithography, photolithography is usually sought for finer, intricate designs where you get precise patterning of your design. So my design is the 200 by 200 layout that is shown here. So here in this design, you can actually see the smallest feature is about 60 to 100 nanometers, and the biggest is 60 micron. So you can see there is a range there. So I have chosen the thermal scanning lithography process for this. And the substrate here is a glass. It is a non-conductive substrate. And it is a DBR, Imagine Mirrors. So that is actually layered by tantalum and silicon oxides. Of about 32 pairs of them are being lined in on top of a glass. So that is my substrate that I would be using for patterning. So the default functioning of this thermal scanning lithography technique is by electrostatic actuation. So you can see it is usually on a conductive substrate where the voltage is applied between your cantilever and the conductive substrate. But here in this particular example, I am using a non-conductive substrate, it's glass. So I had to opt to another mode, which is called pulse heating mode, where you don't have any writing force voltage. Instead, I am using a thermally, it's with the heat, so thermally induced bending of the cantilever. So I adjust the parameters by changing the forward height and also the heating temperature on the tip, the heat temperature there, and the duration of the heating on the tip. So the longer the time, the longer the transfer of the heat to the tip. The writing, how it works is wherever there is dark, that is where it starts writing. Where there is heat, the tip is hot, so it ablates where it has to pattern in the dark areas. In the white one, it's cold. There is no patterning that is taking place. So after development, this is the optical image of the pattern that I have created. Unfortunately, I don't have any high resolution images to show at this point in time. I am able to get precise patterning as designed initially. However, I did have some issues of stitching glitch, which was worse than this, but then I was able to tweak it much better, but there is still some sort of a glitch issues going on. For this particular device, this is not that significant, but there are other projects that I am doing where this is very significant. If any of you have used the equipment or faced similar issues, I'm happy to chat about this after the talk. Now that the samples are prepared, we have sent it to ANU for the testing. So what do you do with the sample? So this is their transfer setup. The cross section here is where the mirror that I was talking about is. You have the patterned mirror in the bottom plane, and you have the unpatterned one as the top layer, which you close it, bring it down. That actually completes your optical cavity. You shine in the light. Here, their initial excitation wavelength is green, and then they are measuring their reflected light, and they also observe the angle resolved spectroscopy, where they are able to get the different modes of the upper and lower polariton resonances. Depending on how they want to tune their cavity, they have already done simulations to understand what the separation gap is required, because they excited by green and they want emissions in the red regime. So how do you tune the cavities further is where I come in, where you can add in PMMA pillars of different size, shape, and height, and also add in some more two-dimensional flakes, because they want to realize the final device as a polariton laser, but in the red wavelength regime. So these are the initial experimental results from the patterning which was done, and they have simulation and experimental results which match, and they do get them. The cavity modes are obtained in the similar wavelengths as simulated. These are other results. It's for 4 micron and 5 micron pillars as well. So they are testing the other pillars which has been sent through. This is just the preliminary data which I'm sharing here. If this testing part is interest to any of you, please reach out. I can put you in touch with the people in ANU because they were the one who did it. The other part of the experiment is where on the DBR, just the plain DBRs is where I can exfoliate the 2D materials. We do have the capability of pick and transfer of the required material and flake. The bilayer MOS2 was also transferred onto a bare DBRs, and they were tested for their coupling mechanisms. The initial results are being studied. So the future plan would be to combine both of them to compare which has the strongest coupling. So to have the DBR pillars, to have the PMMA pillars on the DBR and then have the flake on top, like a floating flake, to see which gives more coupling, or the other way around. So that would be the future plan. A round of acknowledgement is for the team in ANU. So it's Dr. Eli and his team, and that is Sarka, the PhD student who helped in getting the DBR substrates and also the testing and simulations done. I'd like to thank my colleagues at CSIRO and the Nano Fraser R&D team, Jonas, who was really kind and patient to help me navigate through the Nano Fraser system and answering all my queries and questions. So this is me, happy to take any questions.